we discussed the hydrostatic pressure forces for the simplest case, that is on a rectangular vertical wall. However, we have limitations on that. First, the area can be irregular in the real world cases. It is not always a rectangular wall. The surface can be inclined. It is not always vertical. Third is, the plate can be fully submerged. Unlike the simplest case which we have considered last time, the plate can be fully submerged and it could even well be underneath the liquid column. Therefore, we need a generic set of equations to calculate the resultant force. Let us start with a generic diagram which is inclined under the liquid column, that is not closer to the free surface, and also it has an irregular shape A. We will follow the same steps what we have done for the simplest case. Draw a contour at a depth of h. Now the inclined distance is y. Now let us introduce a thickness to this contour and make an area, and we'll call that is the delta A. Now let us find the hydrostatic pressure force acting on this small area. Now that has to be the hydrostatic pressure into the small area. Now the hydrostatic pressure at a depth of h is rho g h, or if we look at the inclined distances, it is rho g y sin alpha. Therefore, the small force acting on this surface, delta A, is delta F is equal to rho g y delta A sin alpha. Now how do we find the total force? Similar to the previous case, we'll integrate it over the total area. Now when we do the integration over the total area, we'll find out that the F is an integral of area of rho g sin alpha by dA. We know if we consider an incompressible liquid, we can take this rho g sin alpha out of the integration. Now we have integration of y dA. Does it familiar to you? Integral y dA over the area. Yes, it is the first moment of area. So we'll do the maths and we'll find out that the first moment of area is ay bar, which is equal to the integral of y dA. Now the equation simplifies to f is equal to rho g sin alpha ay bar. However, in fluid mechanics, we would like to work with the heights, not the inclined lengths. So let us transfer this to the height. See, we have y sin alpha here. What is y sin alpha? It is h. Now when we have y bar sin alpha, that has to be the h bar. H bar is the height from the free surface to the center of area. So our equation simplifies to rho g a h bar. Now let us understand these terms. Now the hydrostatic force on a generic surface which is inclined is equal to rho g a h bar. Rho is for density of liquid, g is for gravitational acceleration, a is the area, total area of the irregular shape, h bar is the height from the free surface to the center of area of the irregular shape. We can check this formula by applying it to the case of the vertical rectangular surface. Now let us look at the location of the center of pressure. We'll do the same thing what we have done for the simplest case. Take the moments about the point O or in the free surface inclinedly. So similar to the previous case, we'll consider the small area and we'll look at the moment from this small area to the free surface. If we consider the moment to be delta m, it has to be y into delta f. Now we know what is delta f. It has to be the pressure into the area. Okay, so we can express delta m as rho g sine alpha into y squared into delta a. Now let us take the moment about O to find the total moment. Okay, we'll do the maths and we can find out that it is rho g sine alpha integration of y squared dA. What is this y squared dA? Yes, it is the second moment of area with respect to the free surface. So our moment is m is equal to rho g sine alpha into I0. Now that I0 is from the free surface. We don't really like it. We like to have IC, that is the second moment of area above the centroid of the object. So we'll use the parallel axis theorem to calculate it. We know the parallel axis theorem is I naught is equal to IC plus AY bar squared. So we'll do the maths and we can find out that the location of the center of pressure is YCP, that is equal to IC divided by A Y bar plus Y bar. Again, we don't like this inclined distances, so we'll consider the vertical distances. HCP, the vertical height from the free surface to the center of pressure, is equal to IC sine squared alpha divided by AH bar plus H bar. What is HCP? Height from the free surface to center of pressure. What is IC? A second moment of area of object at its centroid. What is H bar? It is the height from the free surface to the centroid. So we have two simpler equations for the pressure, hydrostatic pressure force, and the location of the pressure force. We know the direction, it is perpendicular to the surface. So we have completed our analysis.